In this exercise, we will look at the example of a cyclotron. A cyclotron is a device that can be used to accelerate charged particles, or ions. It is composed of two layers of metal plates, and then each of those metal plates is cut in half so that it looks like two half spheres, two half circles. And then the left two half circles are connected to each other, and the right halves are connected to each other. And then a alternating voltage is applied to those plates or electrodes. And then the idea is that ions can move in the horizontal plane in between those two plates. And since these are connected to each other, there is no vertical electric field, so there is no vertical force applied to the ions. And then there's also a magnetic field applied perpendicular to the two planes, to the plane of motion, so that the ions experience a Lorentz force in the plane which will deflect them. And this is seen better in the top view, which is shown here on the bottom. So here on the top view, I show the two plates, and then the magnetic field now is pointing towards you. So that if we take, for example, a proton, a positively charged ion, that moves initially, for example, in this direction, then it will experience a Lorentz force that points to the right. And as a result, it will start to make a clockwise motion, like this. Now this is all still true even if there is no voltage applied to the electrodes. But now if we choose the voltage on the electrode such that, for example, at the moment that the proton is down here, we apply a negative voltage to the top and a positive voltage to the bottom, so then the proton will be accelerated upwards. Right? So it will go this way. And then if it's up here, we flip the polarity between the electrodes again, and now it will be accelerated downwards. And so the proton will go ever faster, ever in a larger circle around the cyclotron. That's the idea. And one of the questions that we want to answer now is what frequency do we have to apply to these plates in order to make sure that we accelerate this at the right pace. So in order to answer that question, we will look at the force that is applied, which is of course the Lorentz force. The Lorentz force we can write as such: F vector equals Q times the velocity vector outer product the magnetic field. And the outer product you've seen in the theory lecture. Make sure that the Lorentz force is always perpendicular to both the velocity and the magnetic field. Now the magnitude of the force we can write as follows: F equals Q V B sine theta, where theta is the angle between the velocity and the magnetic field. But in our situation, the velocity is always in the plane of the cyclotron, and the magnetic field is exactly perpendicular, which means that theta is 90 degrees. So in our case, we can simply say that F equals Q V B. Now in our situation of the cyclic motion, the Lorentz force will take the role of the centripetal force. And the centripetal force we know as mv squared divided by r. So we equal that to QVB. Okay? And then we see that on both sides of the equation there's a v, so I can cancel this v to this square. And then I can solve for r to find r equals mv divided by qb. So this is the radius that once you have found a certain velocity, once the proton has reached a certain velocity, you can now calculate what radius corresponds to that velocity. But we're interested in the frequency or the voltage that we need to apply. So let's look at that velocity a little bit differently. We can also say that the velocity of the proton, v, is the circumference at a certain point, so that is 2 pi times r, divided by the period of motion, the period that it takes to complete one revolution. If we now substitute the r that we found here in this expression, we find that this v equals 2 pi mv divided by q times b times t. And interestingly, we see again that there's a v on either side, which we can cancel out. Right? So now we can solve for t, the period, t equals 2 pi m divided by qb. Or the frequency, which ultimately we are interested in, the frequency f, which is nothing but 1 over t, equals qb divided by 2 pi m. And this is a very interesting result, because what we see here is that regardless what the velocity of the proton is, regardless what radius it has reached in its process of being accelerated, you always need to apply the same frequency. So you can just start with a proton that is almost at still motion, and then start with a certain frequency, and you don't have to change the frequency, and the proton will just be accelerated more and more, which is very convenient. Okay, so now that we've found that, let's look at some real numbers. So we take the numbers from one of the biggest cyclotrons in the world, which is in Japan. You can look this up on the internet. So that cyclotron has a radius, capital R, of approximately 10 meters, and a magnetic field is applied of 4 Tesla. Now imagine that we will accelerate a proton with that cyclotron. What kind of velocity will it have reached by the time that its radius is as big as the cyclotron itself? And for that we will use this expression over here, but now solved for v. So we say that v equals q times b times capital R, because we're interested in the point where the proton has reached the maximum radius, divided by the mass. Okay, if I now fill in the numbers for a proton, we take a charge of 1.6 times 10 to the minus 19 Coulomb, times b, which is 4 Tesla, times the radius, which is 10 meters, divided by the proton mass, which is 1.6 times 10 to the minus 27 kilograms. Now, though, very conveniently we find there's a factor 1.6 both in the numerator and the denominator, which we can cancel. And then on the top we see 10 to the minus 19 times 10, which is 10 to the minus 18, divided by 10 to the minus 27 is 10 to the 9. So in the end we very simply find here 4 times 10 to the 9 meters per second, or 1,000,000 kilometers per second. Which is very fast. If you think about it, this is even faster than the speed of light by a factor 10. So there must be something wrong. It cannot be possible that with a cyclotron we can accelerate a proton to 10 times the speed of light. So something is going clearly wrong here. What is going wrong, this you will learn in your physics studies if you choose to follow that, is that as the proton approaches the speed of light, its mass will actually increase. This is what Einstein predicted. So you have the rest mass of the proton and then an additional mass due to the high velocity. So at some point it goes so fast that it becomes harder and harder to accelerate it more, and you can never reach the actual speed of light. So in a real synchrotron, at some point you can no longer leave this frequency constant. You have to start tinkering with that frequency in order to compensate for these relativistic effects. But this is far beyond the scope of this course. And with that, we conclude this example.